Hello everyone. Today we are going to cover a lot of essential microservices architectural details like resiliency patterns, ingress, distributed tracing. In case all these terms that I have written over here, they sounds kind of alien to you, just stay with me till the end of the video. I am sure you will get a very good idea, and not only a good idea, you will get a completely a senior engineer or a architect perspective how a microservices and the distributed architecture should be created, and from a junior engineer's perspective also how this different orchestrations around the microservices can be written on a very low level code. So let's start with a very basic example of an incident, and why we need this sort of things like the resiliency pattern, the ingress, the distributed tracing. We will start from this example or this real life or a scenario based use case. From there we will build upon our intuition, and gradually we will come around all these popular terms that we are writing. Then we will find that behind the scenes of this popular term, it is just kind of a design or implementation patterns that are in place. So suppose there is a user or a user facing client app you have, and this user is interacting with your system via their mobile application. So you have deployed a mobile app, and this mobile application is again calling your APIs. So suppose you are running a fintech application, and in your fintech application you have a transaction API. So you can think something like a GPay or a PhonePe, and you have a transaction API in place. So that transaction API, they inside its own pattern, what it have is it is calling something like a account service, and on the other side it also have a kind of a composite service which helps you to communicate with the account service. So composite service is again kind of a service pattern we have seen in one of our earlier videos, that while we are dealing with this many number of APIs or this many number of service, we generally create a composite services around this. So our account service is a primary one which deals with the database. So you have a database in place. That database is in Postgres. Okay, one RDBMS database you have, which is in Postgres, and whatever the data this guy need, it goes to the Postgres, and it takes the data back. So now this is the whole architecture. Now what has happened in your case is your system architecturally in a timeline like 11:47 p.m. just before midnight, it is working totally fine. You have a TPS or the transaction per second of 450, which is quite a good number, and in your machines you have a CPU of 35% and a memory of 50%. And if you are kind of not very sure about this term, CPU is basically tells you that suppose it wants to perform a calculation and executing the instruction. So how many like how many percentage of the actual CPU memory is being taken? That is the number here when we talk about the CPU, and memory is here nothing but the RAM. Like when you are talking about the 50% memory, that means the 50% of the RAM is occupied. So this is your processing capability, like what amount of the processing capability is being taken. So if you see this number, these numbers are pretty okay right now in my system in that given timeline. So after this happened in a certain time, right? So after this, we just started seeing some kind of a slowdown in the system, that gradually in some more time, suppose sometime around 11:52, in a 5 minutes time, what has started happened is this account service Postgres that we have, it actually have some issue, and the system has started behaving. How do we actually come to know that the database is slow? So when we see the connection pools that are being used by the application while interacting with the database, we see the 18 out of 20 that is exhausted in a certain point of time, and the latency, it started spiking. It is from 250 millisecond, which was the earlier one, it is coming around 5 seconds. So this is the standard response time that we started getting while interacting with the database. So this is the part, this is the exact part which started giving us problem. Okay, we still don't know what exactly is the issue yet. So what we started doing it, we as an engineer start exploring what exactly has happened and what exactly is the call chain is. So we found that, like in our next phase, we found that there is a sync dependency issue that is happening. And in this sync dependency, there is a transaction composite we have, right? So this transaction composite, what it is doing is it calls the account service for the syncing purpose. And there we see that a certain REST client that we have, which is making the call, it has a timeout set to suppose 30 second. Okay, and we are seeing that it is reaching that timeout, and our system is getting slow gradually over the time. So the thing that started happening is, like, if we have to just understand from the logs, it is basically happening a thread pool saturation. So in the thread pool saturation, what happens is, like, one request hangs for 30 second, this sort of thing, and there are 10 requests arrives, then they remain in blocked state. So what happens is, all the 20 thread pool that we had earlier, all of them are in blocked state, right? And in this process, the future transactions are also blocked here. And here we start getting something called a complete cascading failure, because my current 20 transactions are blocked and taking away the whole threads or the available thread pools, and this leads to that particular user impact that we were talking about. At, like, by the time this thing happens, like in just a 5 minute period of time, suppose this happens somewhere around 11:58. Okay, so by this time of 11:58, we found that the system is in a increasing failure mode. Like, we started getting the HTTP 500 error. We are seeing a huge false, like in terms of the financial transaction, like 1250 plus false in that 5 minutes time. There are a lot of tickets are getting raised. So this is a exact scenario that we see when we are handling like a 2 a.m. production incidents. Okay, and further this, the complete detection process started, and then we found that because the error rate is beyond 50%, so alert has been created across the application or the application management. I would say that every engineer or the corresponding manager who are responsible for this section of the application, they start debugging at this point of time, like in the midnight, and they found that the database, they haven't found the database reasons yet. So initially, generally, when somebody gets this sort of error rates or some sort of a staggering amount of time when some service is not working, first thing generally anybody would do is they would go to the Kubernetes or into their distributed orchestrator architecture, and they would just restart the account pods. Now, what exactly is the pods are in Kubernetes concept? So pods are basically the smallest deployable unit in Kubernetes. So Kubernetes is a orchestrator, which you can think like there are multiple computers are there, and all those computers how they interact with them, and you can actually take down one computer and just bring another computer to work with you. This sort of a orchestration Kubernetes provides. And here, in our earlier video, the stuff that we discussed about the containers and about the Docker, so all those containers run inside these computers, which we call in Kubernetes language as pod. So pod is what? It's the smallest unit in the Kubernetes, and it represents those containers that we have built earlier, the container images, and generally they kind of share a storage or the network, and it is a logical host. So pod that we have, you can think of a computer or a logical host in Kubernetes cluster. Okay, and the services around it is abstraction, that this how this set of pods has their networking done. So if you have a computer or a host somewhere in the place, you need some sort of a networking layer, right? So that networking layer is known as the services. Okay, so this is basically the networking layer that we are talking about, and who controls how these pods behave is called the deployment YAMLs. So deployment, these are the one that manages the desired state. Okay, it manages the desired state, and it enables the updates, the scaling, the self-healing, all the things that we have in Kubernetes. So Kubernetes, we are not really taking a lot of dig right now. If required, maybe I will create another independent session on of how Kubernetes works. So whenever this sort of error happens, one of the first thing generally engineers do, and always not for the right time, they do a pod restart. So they come and restart the account pod, and they also think that maybe if they scale the composite to some replicas. So when I say replicas, means like they could just keep on increasing the number of pods that are used in the whole distributed process. So this composite replica that we have, this replicas, we are going to like create 10 more replicas and think that whether it is actually going to solve the problem, but it will not solve, because ultimately what has happened is this is the bottleneck right here. Completely the thread pool got exhausted, and if there are more requests coming from the composite service, like if composite service has some kind of a more replicas in there, then what would happen is these guys will have further more thread pool consumption, and it will make the system far worse than what it is already. So now gradually we understood that there is a certain service or a certain table we have created, that table earlier having no data or no hit, but due to our feature enablement, what happened is our mobile applications, this transaction API started calling that or started filling that new table. Okay, so that new table has no index in place. So when it is inserting, it is still okay, but when it is fetching from that data, because it doesn't have any index, so it started getting very slow, and ultimately we get all this cascading failure. So here what we create is like we contact the DBA, we create the index, and the incident has been mitigated like this. So by the time all this thing has happened, probably like the issue started around 11:47, right? Suppose it is already around like 4 a.m. in the midnight. Okay, and it is a very high severity incident that has happened, and it has led to so many losses. For example, there is a failed transactions of uh, 8,000 plus. So you can think that uh, when the GPay is failing in this way, the people are shifting to the other application. So it is a complete loss of a particular application or a particular product. Like whenever it is not serving the customers in a right way, in the current day and age, the customers, in case they have an alternative, they will just go there and they will stick to it. So this is the failed transaction, the kind of the revenue impact we had, that is also very high. Also, like in the app store, people will go and they will just give the negative reviews. So that would even that would even take the review very low, and it would not let the other user to get onboarded first. It will be very difficult to convince the new user that if there is one app with a 4.8 star rating, why somebody would install our application with 3.7 star of rating. So this sort of issue do happen very often in the distributed system. And the thing that you saw here, that this resiliency of this part, that when something is failing from this part, we do not have any resiliency of that particular error in our level. And whenever any error happens, you see this error completely traveled to the end user from this layer and make all the servers or all the services kind of non-operational. So this is the exact thing that we call as a cascading failure. So this is the exact term of this thing. So cascading failure is like, since the distributed computing came in the picture, this has been one of the most talked about thing, and most of the system have been suffering for this. So whenever we are extending our application to a microservices level, this sort of cascading failure or making the other layers resilient, that is very very important. So if we just do a proper post-mortem, that what we just analyzed, what we had is, like, the problems that we had is, the first of all, there is no circuit breaker. Now if this term is new to you, let me tell you what a circuit is or what a circuit breaker is. If when this complete plain request, when it goes from here to here, okay, like getting through the transaction, through the composite service, through the account service, and this is the complete circuit, because it comes like this, and the data goes here, from there data goes here, from transaction API to this. So because it has a complete request response, so we can call it as a complete circuit. So now over here, what has happened is, our transaction composite service that we have written there, it continued calling the slow account service there. Although the account service was getting choked up, but still it keep on calling that, and every request waited for like 30 seconds. The thread pool, the thread pool completely got exhausted, but still we kept on serving, like, or sending the traffic. Although the thread pool of although there is no thread pool, but the system keep on sending the traffic again and again to the downstream ones, like, or the upstream ones, like for example from the transaction composite to the account management or the account service that we have. And it didn't have any configured timeout in place, that if it is the default REST client that we had, it is timing out in 30 seconds, right? Rather it should be around like 5 seconds, because the moment we are putting something as 30 seconds, that guy is blocking the thread for 30 seconds, right? So 30-second blocking of a given thread, that is what exactly started happening. So this is the particular thread pool of a given thread pool, 30-second blocking was happening, so the request keep on piling up. And this is something like we will discuss further called bulkhead, and how can we avoid this through our resiliency pattern. And here also, like, we do not have any intelligent retry or any sort of a resiliency to the that one time if the error happens, let's fail fast and try again. Those sort of things are also not there. Like, it should fail really fast, like 2 to 3 seconds, and let's retry again to see whether we can succeed through our calls or not. And again, as we were getting like a high number of requests, so all these requests, they were getting piled up. We were not making any sort of rate limit, that when we are seeing that our requests are getting piled up, we need to create a back pressure of the traffic. Like, the traffic as it was keep pouring in, we need to maintain a back pressure to make sure that we are not serving any further traffic. And also, had there been a proper distributed tracing mechanism in there, so tracing means like what happens in this whole circuit, we get a singular view, that if from mobile a certain request comes, and what exactly is happening during our this transaction API, what is happening for that particular request. Suppose a request hash, this is coming. So how this request is traveling through each of these layers, those ideas we are not having on the very first place. That is called a system wide tracing, like a distributed tracing. So in distributed tracing, what happens is, like, we know that if a request has originated and if it is reaching into the database or whatever the other layers, what is happening from start to end. And alongside that, also, if we had some kind of a proactive monitoring, okay, because our thread pool was already getting exhausted, that's a very big sign of a system cascade failure. So we did not have any proactive monitoring in place, where we have all the system coming together, and they are telling that there might be a bottleneck that is getting built up. So these are the things that we must have in place to make sure that our system works flawlessly. And over the course of this lecture, we will try to build all these details, that how we can actually resist it. And we just discussed earlier as well, right? This is the amount of loss that we have to suffer as a product or an organization, just because of this index not getting created, or the index was not created where it was actually meant to be. So before going on to the next level, let's revisit what exactly the architecture of this application have been. So we have a mobile application in place, right? So in this mobile application, we have 4 endpoints to interact with. So the endpoints are something like this, like the first one is the for the account, the other one is for the transactions, the another one is for the fraud, and the one is for the composite. So you see there are different HTTPS calls goes, one for the account, one for the transaction, and here we have to maintain different TLS certificates, that is the transport layer security certificate, to make it under the HTTPS. So that is the difference between the HTTP and the HTTPS, right? So in HTTPS, we are going to have this TLS certificate in place, and this is going to be my so these are going to be total 4 different HTTPS call that we are making. And also, in case we have to create another new service like this notification fintech, suppose we want to subscribe to notification for some reason, and a new microservice has been added over here. So in that case, we have to get another new TLS service, we have to create another new entry. And these are these are the basic, the DNS or the TLS management. Suppose they are hosted somewhere in the GoDaddy or any kind of a platform which provides us the DNS. Now it goes through the Route 53 of AWS infrastructure, and through Route 53 goes inside the AWS infrastructure, and then again we have separate load balancers for all of them. Like the for account fintech we have ALB, for transaction fintech we have another ALB or the application load balancer, and again for the composite we have another ALB. So they have their own target group, and in the actual Kubernetes architecture these things comes to the pods, like the account pod, the transaction pod, the fraud, and the composite pod. So now the problem with this architecture is that for a single service that I have, like my complete application, there are this many number of DNS and the TLS management I need to do, and there are this many number of different ALB. Like one ALB definitely can have multiple target groups, but this many number of different ALB I have to control, and this many number of pods which are still fine, but we have a big overhead at these two layers. And what exactly is the request sequence? When a certain request goes, it has to go through all these layers. Like from the mobile app, it goes to this HTTPS layer, then throughout 53, it would go to ALB, then target group, and then it goes to pod. And the similar way, the complete circuit that we are talking about. So it keep on going back from here to the mobile app. So from the complete aspect you will see there are so many issues there, like in terms of the total infrastructural overhead. There is a different ALBs, there are different domain name services we have to maintain, there are different uh, all like 4, or in case we have a new microservice it will be 4 plus x if x new microservice we are writing. So this is the kind of a pattern that we end up having, and same with the TLS and the ALB target group interaction also. But all these things, there is a very simpler pattern which we can actually replace with is, like we can have a single ALB, and with the Kubernetes Ingress controller, we can have a internal service mesh. We will again come detail about it, like what exactly is a service mesh, and we can have a API gateway pattern. So with all this thing, we can actually replace this whole architecture in a very simplified way. But before we go into the Kubernetes or the details around the Ingress controller, let's take a step back. We need to have a shared mental model without any confusion regarding the Kubernetes networking. So in that case, there are some important load balancer related model I am going to introduce. So the traditional load balancer, when we are talking about, what do we actually mean by it? So a traditional load balancer is a component that receives traffic on a single endpoint and distribute, right? So we can just think that there is a single endpoint where it receives the traffic and then it distribute with some logic. Like there can be logic of round robin, there can be logic of weighted transitions. Now, if you think about Kubernetes, in a Kubernetes cluster, similar to like multiple services or multiple app servers behind a load balancer, we do have multiple pods. So this can be one pod, this can be one pod. So in this way, there can be multiple pods in a Kubernetes cluster. And over here only, Kubernetes uses this something called a abstraction, some sort of an abstraction which we call service. We will talk detail about what exactly this abstraction is. So this service abstraction to provide a stable endpoint. So this abstraction that we are talking about, this guy is only a stable endpoint which would make sure that through which we can go to the pod. And why this abstraction is required? Because pods are ephemeral in nature, so that means the pod can die anytime. If we have a definitive IP addresses given on for each of this pod to my load balancer layer, then we will be in trouble, because the pod can die anytime when they restart their IP, or the other corresponding internal details might change. So this this is the thing we have to remember, that the pods do change, and this is our stable service of IP or DNS that we are talking about over here. Now, uh, this is the very basic thing that we could think through, that in the Kubernetes context, we have this sort of a stable service and IP or DNS, whatever we have, that we call in Kubernetes concept load balancer. And how it looks in the code, we will see in a little bit more time. But let's again clear this mental model up. Now, the next step we want to take in the service is cluster IP. So cluster IP is the default Kubernetes server type. Like, it creates a stable virtual IP and the DNS name that is reachable only inside the cluster. So as I said, like the pods change, or to be more precise, like pods come and go. So having that definitive stable addressing and basic load balancing, that is what we call is the cluster IP. All right. So from now, if anybody wants to reach out, suppose my own DNS for this cluster IP is something like api.svc.com. Okay, so we only reach out to this, and then it is a responsibility of those cluster IP to divide the traffic based on whatever the logic I have written. So load balancer, again, it tolls uh, like it let you come via something, and all these things, as I was talking about, this happens inside the cluster. So now if I have a, so cluster IP is the first one. So now in case I do have a public URL to hit like this, cluster IP won't help us because this is inside the cluster, right, which is completely abstracted away. So to make a cloud provider reach out to my cluster IP that we were talking about. So this one is our cluster IP, right? So what we can do is we can use something called again, it's a very generic term. We have a load balancer service of Kubernetes itself. So it provisions an external IP. So over here, an external IP would be provisioned, and this external IP can be used to forward the traffic to my cluster IP. And and how it practically looks like for different clouds. So for example, if we are talking about AWS, in AWS we can have ELB, like the elastic load balancer. For GCP we have the GCP load balancer for the Google Cloud. So all of these things can be our external IP, and these guys are going to forward the traffic. That's all. But again, the problem is, in case we have like 20 microservice, in this case, if we have 20 microservice, then we need 20 external IP. One single external IP cannot point to multiple microservice. That is the part, is the key of our transition. So this is a very inconvenient thing. Like, so with 20 microservices, as we were discussing earlier, like we have to uh, think about their DNS entries, their TLS, and there are a lot of cloud operational overheads the moment we are following this external IP one. So at first we discussed about this cluster IP. So cluster IP is again is a good one, but what it would do is it will completely work inside the cluster. So we need some sort of a way to reach those cluster IP to do the actual load balancing. So for that, we can use an external IP and forward the traffic to our cluster IP. So this pattern is called like the actual load balancer pattern. But the problem with this load balancer pattern is, like, if I have 20 microservices, for those 20 microservices, I will need 20 external IPs. So to solve all of these things, we have Ingress, and in the Ingress, we need to just route to a single point, and that route is going to magically take care of uh, distributing or take the outside cluster traffic to the internal services using rules and the host. So these are the few things I'm just writing away for so that we do not have any confusion around it. So ingress is nothing but it is not a particular object or particular machine or a pod. It is rather a simple K8 API. What it does is it exposes the HTTP or the HTTPS routes from outside the cluster to the internal services that we have. Okay, this is pretty much what it does. Now, the number one confusion to kill. So the confusion to kill, I would say, is ingress is just rules. Okay, how does it magically implement the distribution or the redirection of the traffic? So ingress is just rules. It does it does nothing by itself, and you need an ingress controller to implement those rules. So the controller that we are talking about, like the ingress controller, this is the important part, and this ingress controller are required to implement those rules. That's all. This is the primary confusion that we need to like we need to eradicate from our mind. So ingress is mainly the HTTP or the HTTPS routing. It doesn't expose any arbitrary ports or protocols the way we did it for the load balancer earlier. And if you see just a demo ingress how it looks, I would like to bring to your attention all this part, like the slash web or the slash API. What it does is, like, based on whatever is there in my HTTP URL, it is just going to route based on that. That if it is slash API, it is going to take to app SVC. If it is slash web, it is going to take to web SVC. As simple as that. So now we have one entry point and routing rules that sends the slash API to API service and slash web to the web service. So this is all about like pointing from one end to another. So now let's see via a diagram how everything comes together, like whatever the things that we have been discussing. So at first we have a web plus API, and this is this web API that we have, like we have developed it for ourselves. Okay, so this is kind of a website that we have in our disposal, and now from outside the world we need to access it. So how we will be accessing it? Like we have a client or a browser in place. So this client or a browser, it is going to come to some sort of a external load balancer at first. So once it come to the load balancer, then further it will be looking up to our ingress rules. So this ingress rule, this ALB or whatever, like the application load balancer, will generally will generally read through the K8 APIs, and further there will be distribution of traffic happens towards the cluster IP. So this is what exactly would happen. Like after this ingress rule gets applied, it would come to the actual ingress or our cluster, and over here the ingress of HTTP routing rules would happen, and our slash web will take to the web.svc. Our slash API would go to API SVC. So in this way, the complete routing rules will be taking place here, and all these things, this two that we are talking about, this two end of the day will be the cluster IP. So all these services will have their own cluster IP, and thus exactly in this way all of these things comes together, like the client browser, from there it will come to the ALB, the after from the ALB it will understand what exactly is the ingress rules are, and based on the ingress rule all the HTTP routing inside the cluster will happen to the cluster IPs. So the same concept, if we start applying here, you will see like there is a great way to optimize it. Like now we know that instead of maintaining this many number of application load balancer, I can just have a single ingress, and that ingress controller will make sure by applying the ingress rules that which particular pod I want to reach out to. So let's see how would the architecture look like. So now that we understand what exactly ingress is, let's take this example further, like the one that we took up. We will gradually take it to the ingress concepts and see how easy it becomes and how it is able to save a lot of cost and a lot of operational complexity for us. So over here we have our mobile app, right? So from this particular mobile app, we are going to route our traffic to our backend web services. So this mobile app is the source of our endpoints, and how those endpoints are like this for the account, transaction, frauds, and composite. And it is something like this is going to be our base URL, this particular base that you are seeing. This base will be something like this: www.api.fintech.com. And then from there, we are going to hit our DNS. So from here we will come and hit our DNS, and what this DNS would do is, like, it is basically not only DNS, this is DNS plus TLS, I would say. So over here, the if I have to go to the api.fintech.com, where exactly should I go? Like whether it is via some Route 53 or some other sort of a routing, like Azure Traffic Manager in case of it is a Azure Traffic, all those decisions it will be taking from this layer. And then just as we were talking about AWS, think that here we have the Route 53, and by going through the Route 53, it knows that it has to hit some point in the AWS infrastructure. Now, in our AWS infrastructure, we already have a consolidated ALB. Like, I'm writing it as a consolidated ALB, but it will be a simple ALB only. And this consolidated ALB is actually provisioned by our Ingress controller, right? Like, I'm again just doing a little revision. So this Ingress controller will listen to our Ingress, and using that it will create the necessary ALB. So it will create and configure this ALB to with the rules and the targets. Okay, so all the rules plus target that we are going to have, it is going to configure the consolidated ALB on this. So now you see the kind of improvement we have from our previous architecture is, we had this many number of ALBs over here and this many number of Route 53 DNS, all these things configured. So from here, I came to a single consolidated ALB. Now from this ALB, uh, further it would go to our actual Kubernetes cluster. So now the actual cluster mapping would start. So this is the area that we are talking about. This is the K8 cluster. So what would happen in the K8 cluster is, the Nginx ingress controller already have given all those rules to our ALB that in case you are coming into accounts. So this would make sure the forward of the path. For example, from using this rule only, the path of accounts, what it do is it will find out that what exactly is the cluster IP for the account when we have declared our pod and the other load balancer configuration. So suppose from here it finds out that this guy should go to the account service with a cluster IP, with a given cluster IP. I'm just writing it as with a cluster IP 8080. Similarly, the other ones, it will probably go to something like transaction service. Okay, and this would go to again transaction service. So this is only transaction, not fully transaction service, I would say. So in this way, all of the corresponding ones will get forwarded to all this 4, and further, like I will just extend it. What would happen over here is this guy, based on this rule, it will go to the corresponding pod. Like over here, suppose the pod is like our account pod, this can be our transaction pod. So based on this, all this pod will be added. And now the advantage that we will get is, suppose we have a new notification service to our disposal. So only thing we need to do is we need to come here and add our notification service into this slash API slash notification service. And this notification service is going to be just a new rule. Over here we are going to define that you take it to this particular path of notification service 8080. So, and now it becomes like a super simple. It will just forward it to another this three layer, like the path, the transaction, and then the pod. So now you understand, like if we have a ingress controller, how easy it becomes to manage all the things in a centralized place. So earlier, like we started off with a incident, and from that incident we kind of came to a discussion that how generally this particular architecture would look like if we do not have any sort of a ingress in place, and then gradually we introduced ingress. So I could have just told you that this is how ingress works. Why I took this longer route is because this intuition had to be developed, that this many number of cost, like for 4 ALB, like 4 different DNS and the TLS certificates, all of these things we need to handle if we follow this architecture. And with this particular ingress architecture, we have a single DNS with a TLS, we have our a single consolidated ALB, and within our K8 cluster we have all the rules defined in our ingress. And the moment we want to make any change, we can just make a change into the rule, and the traffic will automatically start redirecting as we wanted here. So now coming to code, if in case your application or anywhere you see this sort of a implementation, that you have this load balancer implementation, that is kind of a bad implementation, because now you know, for every service that you create and every load balancer that you create, you are going to provision a new AWS ALB for this. And this particular approach would just introduce additional complexities into your application, and it is kind of a non-extensible as well. As we saw, like if I have to create a new notification service, how difficult it becomes when we create separate load balancer. Rather, so here, when we will apply our kubectl, we will see that there will be 4 different controller will be created. And for this, the main problem, as we talked about, there will be 4 different DNS configurations as well. So this will be the kind of a DNS configuration we are going to have, 4 separate DNS. And as you can see, like the cost will be like literally 4 times for each of these cases. So there will be 4x cost and there will be 4x complexity in this approach. So rather, what you will have here is you will be able to the moment we shift to Ingress, our implementation would look like this, that we are going to have all of our endpoints defined like this under our Ingress. That we have over here, you can see we have our accounts, we have our transaction, and what are the services that where exactly we will be going to. So this service again will be our actual cluster IPs that we were talking about. So all this account service or the transaction service, they will be some sort of a cluster IPs like this. Over here you can see this is a cluster IP, this is the app of account service. We are going to have something like this. And with this, when we deploy this one, or when we do kubectl apply, only a single ingress will be created over here, in opposed to what we have seen earlier. Like for different account service there will be separate load balancer. So now there will be a single ingress, and this ingress is going to control all of the things, like when you put it with your helm chart, and through service account you can create your AWS ALB or the application load balancer through it. So that's a different sort of a discussion, but this particular approach is very important on simplifying our architecture. And why I have spent this much amount of time just to understand the ingress, because this is where many application developer or many architects, they somewhere get into a problematic area, like how exactly architect this sort of a microservices. So that is why I wanted you to understand with a load balancer and with Kubernetes how exactly the modern microservices architecture works. So now that we kind of optimized our infrastructure, let's talk about the resiliency or the resiliency 4J pattern. So resiliency 4J is again kind of a library or a framework that we are going to use. So there has been a deprecated ones that is called the Netflix Historics. So from there we came to the resiliency 4J. So even if you are using the legacy one, few of the concepts would still apply, but I would strongly urge you to learn the resiliency 4J one only. So let's take like what exactly happens during the first statement that we started at the at initial example, like where we have the CPU and the memory usage, everything is coming fine, but still the database was running slow. So I will just revisit this example with some pointers. So what have happened is, like we have a microservice going on, and our account service does make a Postgres SQL call, which is for some reason without index, it is becoming like 3.5 seconds. And mind it, like for the production grade scenarios, 3.5 second per request is a lot of time. So we have this transaction composite service. So this transaction composite service calls our account service, and in a synchronous manner, like not exactly in a asynchronous way, it calls kind of a synchronous manner. And we have a default 30 second of timeout, like if it is waiting for 30 seconds, then it will time out the request. So now with this approach, what would happen is all of our thread would get exhausted, because uh, none of the queries would get past this, right? Like the request will just come one after another. So one request come, it will wait, and another request come, the longer wait time. So in this way, like the more request comes, the wait time will be more longer, because the other threads are anyway waiting for it. And in this way it would introduce a kind of a cascading failure across the full microservice. So now in your microservice architecture, what we need to do is we have to create a layered resilience. And what do we understand by layered resilience? So it is in multiple layer we are going to apply our resilience. So for example, when some sort of a user request comes, so user request comes to our time limiter. Okay, so at first it comes to the time limiter, and this time limiter would enforce a overall timeout. So this is like a overall timeout across the application. Okay, so the next layer would be our rate limiter. Rate limiter, what it does is, like it makes sure that within a sliding window, that within like a 60-second time, only X number of requests. That is what this rate limiter is going to impose into system. And then another important point is bulkhead. So bulkhead is when we have a single failure, like this account service was our failure here, right? So it is bulking the whole head and making all these applications the rest of the parts waiting. So what is what it would lead is to kind of a complete level by level failure. So we have to have a isolation of the failed service. So if any service is failing, we have to fail them independently. So it should not make the other services fail. Then there comes the most important thing, that is a circuit breaker. Like in case the failing service or this bulkhead is causing a lot of traffic jam across our application, we have to break the circuit of the calling. Like the moment we see that there is a multiple 30-second timeout or something is happening, we have to stop calling the failing service. And then of course there will be things like retry. So sometimes happens that like for some sort of a DNS failure or some very momentarily system request spike, one request might fail. So we can always do a retry. So this is going to handle the transient errors in this. Okay. Now along alongside all this, there are some other very important architectural decisions. So all these things that you are seeing, this is basically the architectural decisions. Like not a single person, like for the big tech organization, they take this decision. Rather, this is like a group of architecture review board. They decide that how this pattern should look like. For the startups, it's fine. Like if there are one or two engineers are working, that's a completely different ball game. So all these things, and there is something called graceful degradation, that in case my system is not working properly, uh, the way I will degrade my performance, or the way I am going to respond back to the user, that I'm not going to lose my customer then and there. Okay, so the graceful degradation or kind of a fallback, we also have to support. So all these things comes under kind of our architectural decisions, and these decisions are the core of the microservices architecture. So when you study like any microservices book or any big system, you will see all of this 5 to 6 patterns which comes together, and it is going to make it is going to decide when exactly to make your system, or when exactly to break your system, or at the time of breakage how exactly your system would behave. And the core of this complete concept is circuit breaker. So when we discuss about circuit breaker, there are multiple terms you will come across. One is the circuit closed, another one is circuit open, and another one is half open. So we will now see what exactly this open, half open, and circuit close means. So circuit close means like the all the things are working in a normal flow. For example, like if I have to draw a parallel to the electronic circuit, that means my actual appliances across the circuit is working fine. So like this means the system works fine. The moment the circuit gets open, that means the trip needs to break. So break the trip, and it is going to protect our system from those cascading failure sort of a thing. And after a certain period of time, we are going we are also going to check this part of half open, that test if it is safe to close the circuit again. So once we break the circuit, is it okay that if we now close the circuit? That is something we are going to consider under the half open. And for all of these things, we have different criteria. Like when we see that the system is completely working fine, all of my health check and the response that we have in place working normally, then the circuit is closed. The moment we see like somewhere around 50 to 60%, so it might uh, vary system to system, like 50 to 60% of calls failing, then we are going to mark it as the failure detected, and we are going to stop sending the requests. So either we do some kind of a stop or a fallback we do. So during this half open period, so after this open period, we keep on periodically test that whether some test requests are succeeding or not. If they are succeeding, then again we are again going to mark it as closed, and if it is failing, we will keep it as open. So we already discussed what exactly happens like when we do a cascade of failure without a circuit breaker. Like all of our, if we do not apply this, okay, if we just keep our circuit open and in case we do not apply this guys, then the account service that we have, suppose it has around 20 threads open to work as a worker thread. So all of our 20 thread will be blocked and waiting for our database, because the database queries have really slow, and all the new requests will queue up, and this would introduce the kind of a cascade failure. And now to use Resiliency 4J, as we started about it. So to use Resiliency 4J, the first and foremost thing that we will be doing is, for the Resiliency 4J, we are going to add it into our pom.xml in pom.xml, all these dependencies we are going to add. And then in our application YAML, we are going to actually define our configuration. So there can be various level of configuration, like all of them we will not be able to take up in this video, and it kind of varies from one application stack to another application's functionality. Like it is totally based on what is the business value the application provides. Based on that, but still on a high level it looks something like this. Like when exactly we are going to fail our systems, like as you can see, the failure rate threshold, the slow call rate threshold, there is a certain wait duration between the transitions we are doing, and what exactly count as a failure. Like there may be some of the failure we can just ignore as an exceptions, those things also we can mention. So this is a pretty descriptive one, and like at the time when you create your Resiliency 4J, I would say that you feed your coding assistant all your business cases, and based on that you do some sort of a chat with them that how exactly you should configure this one. And similarly, like this is only circuit breaker we are showing. Similarly, for the retry, for the rate limit, for the bulkhead, for all of these things we have separate sections where we can mention that what is the max for the bulkhead. Suppose what is the max thread pool size we can do, and what is the, and all these things together will give you the complete control over your application failure mode. So for example, here you see this is only specific to account service, and this particular part is specific to the fraud service. Now let's see how it looks like in the code. So here in the code you can see like we are having our SLF4J, and we just have to keep on mentioning that which circuit breaker we want to use, what will be our fallback method, that all of the things that we have declared over here. For example, here for the account service, the particular service breaker you can apply over here. So this is pretty simple and easy to apply, I would say. And based on this, you can apply the rate limit, the retry, or the circuit breaker, whatever you want in any of your class. Again, as I said, like this Resiliency 4J or the .NET equivalent of it, like Poly, they are quite vast. How they can be used, and they can be used to apply different way across your application. So whenever you come across this sort of thing, make sure that you make like instead of writing your own pattern, you use either Resiliency 4J, or if you are in the coming from the .NET, then there you use something called a Poly, and handle circuit breaker, rate limiting, bulkhead, all the pattern. And that's the video, guys. Like, we have come a long way. We have covered a lot of ground regarding what should be uh, what are the exact breaking patterns of the application, what are the failure modes, how exactly we design application which have a great traffic routing architecture within Kubernetes, and that is the standard which is being used across the organization now. We have discussed about the ALB, from a multiple ALB, how we can go into a singular ALB with the K8 ingress controller, and then also we took some look into our resiliency pattern, where we have discussed about the time limiting, the rate limit, the bulkhead, the circuit breaking, and the graceful degradation. But again, like as I said, for different application, there are so many different use cases on this. So it is best to like treat all of these things independently, and resiliency 4j have a very vast use cases. So whenever you have any kind of fallback scenario to design, this is kind of a must add, first of all, to your application end. And any sort of a fallback or this circuit breaker pattern you want to introduce, you must use this resiliency 4j. In case you have any further question, please drop a question in the comment section. I will try my level best to answer it. See you in my next video. Till then, stay awesome. Bye.